Swayam Prabha. Digital India. Educated India.
So I want to talk about Langevin model. How many of you are familiar with Langevin model? Okay, at least I see one hand pretty strong and bold, and he probably knows a lot about Langevin equation. So this is a very important technique. This will be a very useful technique. So I want to discuss that. So what is it? Okay, or when do we need this model? Okay, so I want to start talking about this. Now, for this discussion, let's just talk about small particles, sort of like sub-Kolmogorov particles, so to make life easy. Okay, so these are very small particles. What's the advantage of these small particles? You can use BBO equations to move them. You don't have to put a grid around the particle. Okay. Okay. So let's say we have a channel or a pipe, and let's say we are doing DNS. It's really not direct. You're not allowed to call it strictly direct numerical simulation, because that term means you resolve everything, including flow around the particles. But let's just use the fact that we resolve all the turbulence. So this is a turbulent flow, and we are doing a channel flow simulation. And in this one, let's say we have particles. These particles are really tiny. Okay. Now suppose if you release all the particles like in a tiny little blob. Okay. So in other words, in this channel flow turbulence, you release a bunch of particles. You don't have to do anything fancy. You just use BBO equation to track all the particles. And since the flow is chaotic, even though they were in a tight pack, they will end up going all over the place, right? So you don't have to do anything. So this is good enough. Direct numerical simulation of turbulence and some version of Bassett-Boussinesq-Osin equation. You may, many times you may just use quasi-steady drag and gravity. Okay, you may not use added mass and other things. In other applications, you may decide to use that, or people have even used Bassett history term. So whatever you want, some version of BBO you put, you don't have to do anything else. You can track particles and you got the answer. Now let's look at the other problem where you're doing RANs of this flow. Okay, your RANs is going to be one-dimensional problem. So in other words, you will have a turbulent flow velocity. And let's say your RANs is really good. You use RNG closure, okay, some such thing. So you got the mean flow really accurately. You got your K, you got your epsilon, all those things. But imagine that you are releasing the particles here. I don't have to say much. It just a little later it will just go here. That's not satisfactory, right? So we really need to know. So what's happening is that this little blob of particle later becomes a bigger blob of much wider. That's the dispersion that we talked about. That's due to turbulence. Could be particle generated pseudo turbulence, or it could be outside turbulence. In this case, since the particles are really tiny, it's the turbulent channel that's making the dispersion happen. So the question is, how do we capture this dispersal of particles while you're tracking particles? Or while you track particles in RANs, you need to use Langevin model. So what Langevin model does, it tries to account for the effect of turbulence using random numbers in some sense. Okay, so it tries to create pseudo turbulence for you, turbulence that you have not calculated, it will try to account for. Okay. Now we can also do halfway. You can say I have a channel, I'm doing LES because the Reynolds number is really large. You say I have accounted for all the large scale eddies but not the small scale eddies. So it's turbulent flow but not quite like a DNS. You couldn't afford to do a DNS, and we have the same problem of releasing a bunch of particles. Now it will spread if you just use LES plus BBO. You will capture some dispersal of the particles, but it won't be precise, right? Because you have missed the small eddies, so you will not get the precise answer. So sometimes you might want to know, I really want better answer. Here there was no turbulence being computed, so we used Langevin model to take care of entire turbulence. You can use Langevin model. Once you understand Langevin model, you could use that to only capture that turbulence that was missing. Okay, so Langevin model is a way to account for the effect of missing turbulence in your simulation effect on particles. Okay, what is it?
What is missing turbulence?
Well, the ones that you did not compute. Say if you do a RANS,
Scales you are talking about, sir.
smaller scales.
Velocity scale, length scale, velocity scale you need to use.
Yeah, so what I was talking about is if you have a spectra, energy spectra, if this ratio, this is in log scale, if the ratio between the Kolmogorov scale and the large scale is too large, then you may say you will do only LES. This is the filter length scale. This, your grid will be only here. There is so much energy subgrid. There are smaller eddies, so you put a grid, say let's say you have a bucket and there are eddies of all sorts, and you put only a grid like this. What about the smaller eddies which are smaller than your grid? They are going to be moving the particle and you didn't compute it. In RANS, you don't compute any turbulence, so you have to account for, that's why these particles just went straight down. If you just used your fluid velocity, which is all parallel, and if you move the particles in that flow, they will all just go, there will be very little dispersal. So here all the turbulence is not directly computed. I mean, in the RANS you try to account for the effect of the turbulence only in capturing the mean flow. But that's what I meant as missing turbulence, the turbulence that you did not compute. In LES you compute turbulence, but only this much turbulence is being computed. This portion of turbulence is not computed, so the question is, how do I take care of that? Not deterministically. I cannot, because I don't know. I cannot calculate something that I didn't calculate, like the effect of something. But I want statistically, the Langevin model should capture the statistical behavior. It will not precisely tell the motion of each particle, but when you use the cloud's behavior, it will be able to account for. So that's the sort of goal that we have. So I'm going to try to look at my notes here and go accordingly. So the one way to think about this is,
yeah. Please again explain the difference between RANS and LES. I think the problem in all the three cases are same, but the detailed analysis we are getting is different. That's what you're saying. The problem we are solving is same in LES, RANs, and DNS.
In all the problems, we have the same problem in the sense that you have a channel, turbulent flow going, and you drop a blob of particles, and you want to know where the blob is. Later on, it's going to be some bigger size. That's the input and the output, the desired output, are the same. But in the DNS, you're saying your grid is so dense and it's 3D, time dependent, all the turbulence is being computed. And I'm saying that in DNS you have all the turbulence you're computing, so just track the particles and you don't have to do anything. In RANs, it's much convenient because you have only one dimensional. In this case, only the y direction is the inhomogeneous direction. So you will solve a 1D steady state problem for RANs, much easier. You will get very accurately, if your model is very good, you will get this turbulent mean velocity profile very well. You can get K profile, turbulent kinetic energy profile. You will get dissipation, all those things you will get, but not all the eddies. They are not there. Now, if you take that velocity and you try to track particles, the best you can do is that all the particles are going to, because the flow is going. You know behind the scene that there is turbulence, there is kinetic energy, there is dissipation, but you don't have any fluid velocity. So the question is, Langevin model will create synthetic turbulence and try to move particles, will give a jiggling. Okay? And in LES, it's a 3D time dependent simulations, but there are tiny eddies which are smaller than your grid. They are there, they are moving particles, but their effect you did not compute.
So we can say RANs only solves synthetic turbulence, which just deaccumulates calculates the deaccumulation of particles. LES solves the deaccumulation of particles, but small of
some portion, some
fluid turbulence.
Yeah,
and DNS solves everything.
Yeah. So DNS solves everything, so you don't have to do anything. LES solves some of it, therefore whatever you're missing, that's what I meant as a missing turbulence that you did not compute. You have to calculate its effect. And in RANs, you will have to calculate the entire effect of turbulence. Okay. One way to think of this is easiest to think when there is no fluid motion at all. So that's why I wrote it as Brownian motion. It happens at very small particles. So in other words, if you have nanometer size particles and you release this fluid, let's say, is quiescent, there is nothing, you just release the particles in there. If the particles are nano size, they will undergo what is called Brownian motion. Okay. So every particle will do the random walk that we talked about yesterday evening. They will go left and right. Okay. And therefore, lo and behold, this guy will become bigger, this blob of particles will become, so that's called the Brownian diffusion. And the question is how one would calculate this is, you say you solve this kind of equation, d by dt is v, this v is Brownian velocity, okay. So you say, okay, every particle you're going to track its position following some velocity, but that velocity will keep changing, okay. The change in velocity every time will be equal to Boltzmann, the kb, some constant, times some random number. So in other words, every particle, you give it a random kick. Every time step, you ask it to go left, right, front, back, okay. But only thing is that this is a random number. This is a white noise process. So the average of this kick that you give is 0, okay. And its mean square value, you will have to give it proportional to your times step. So if you decide to do a microsecond time step or millisecond time step, so you have to choose random numbers every time, so that when you add over a lot of different steps, it average out. When you average over lots of different particles, the random number you generate, dW, this is a white noise process, it will have 0 mean and its variance will be equal to your delta t. So this is what you do, and this Kb is a well known constant to thermal temperature of this medium, mass of the particle, time scale of the particle. Okay, so
why is the mean square equals to dt?
Why is the mean square is dt? It's just that's a technical detail, because if I put if I multiply dw by some factor, that will come out of kb. Okay, so if you use this kb and if you take dw to be this way, you capture whatever people observe experimentally. Okay, so now if you want to use a different dw, you got to adjust the definition of kb accordingly. Okay, so these two, this is just a warm up thing in the sense that this will, if you put in the right temperature of the fluid, mp is the mass of the particle, tau p is the time scale of the particle, it will capture the Brownian motion that you can measure experimentally. So you just have to give the important point is that you create random numbers and you make the particles undergo random motion. Okay, there is no correlation. So the important thing is that in Brownian motion, each particle, each time step moves irrespective of what it did in the last time step. But turbulence is not like that. In Brownian motion, it's like more like a coin toss problem. Okay, so each time you get a fresh kick. But this gives you an idea how to do this, and this is what we're going to do in the Langevin model, is that each particle, when it moves, it will listen. So here there is no bulk motion, so that's why I wanted to start with. There is no fluid motion. Particle just keep getting random kicks each time. But when you track particles in the previous slide, a channel flow, there is a mean flow which tells keep moving downstream. So you got to add that. On top of that, we are going to add this idea, we are just going to add on top of it. One catch is, however, is that our random numbers now must have some memory of the previous time step. If I asked the last time the perturbation that the random number asked it to move to the right, this time I still will move to the right, but with a different amplitude maybe. So how to do that is the key question. Okay, so what we're going to do is we're going to now talk about the stochastic equation. So in other words, we are going to give random kicks to our particle motion. So let's take the simplest BBO equation, a simple BBO equation, okay, where the position of the particle changes because of its velocity, and the velocity of the particle, this is the Newton's law. I am going to write it like this, and I will explain it in a minute. This is nothing but BBO equation, only quasi-steady force and gravity. Okay, those are the only two forces. I am not using added mass, passage history, undisturbed flow force, all those things will make this equation a little more complicated, and that is not necessary for me to describe Langevin equation. I want to describe Langevin equation when everything is very simple. Now this is non-dimensionalized because you have an equation, mass of the particle times acceleration equal to quasi-steady force plus mpg. This is the equation. When I non-dimensionalize, it becomes like this. Okay, when I substitute for quasi-steady and I do some simple divide by mass of the particle, you get this equation. And this equation is very simple in a way, is that you can see that when the fluid is not, if the particle is not accelerating, if say for example you think of tau p is really small, then the numerator must go to 0. In other words, if the denominator goes to 0, the numerator must go to 0. Okay. What happens when your numerator goes to 0? You will see particle velocity, everything is a vector quantity, is simply equal to, and I will describe what this means. Yeah, so this should be plus. Okay. Okay. So for very small particles, this you see the at sign simply means the fluid velocity at the particle, because if you have a bucket and fluid is changing, we are asking what's the fluid velocity where the particle is. So a small particle will move with the fluid, plus if it's a little heavier, it's going to settle down at the same time. So this is the settling velocity, it's in the gravity direction, vertical direction. So for small particles, the answer is pretty simple. You can even, for Langevin model, you could think of it this limit, you can even think it this way. Now the real question is, what is the fluid velocity at the particle position in the 3 examples that we saw? That's where the problem lies, right? In this case, the fluid velocity at the particle position will be as good as you could ever get, because all the eddies are there, you are computing everything. So you have done a DNS. In this case, the fluid velocity that comes from RANs is just a mean flow, it misses all the eddies. In this case, you have big eddies effects in there, but small eddies effect is not there. So the question is whether you take this equation for a very small particle, or for a larger particle whose Reynolds number is finite, you could use this yellow boxed equation, which is more accurate. No matter what, the question is, we have a problem with fluid velocity at the particle position. So the idea is that now we have to modify the equation so that we have particle velocity acceleration is whatever comes from your RANs or LES, you must add a random so this is what we are going to be working towards, how to model that perturbation. That u double prime is fluctuation that you are not computing, therefore you must create by some random number, and the Langevin model will give you that every time step. It will say here is some added velocity, that is the effect of the missing turbulence that you did not take into account. Now the u double prime is 0 in a DNS because you don't need it. The other thing is this model comes from Pope's original idea. Okay. So what do we need if the turbulence is isotropic? The question is, what should we desire from this quantity? So we are now, I reduced the problem to saying that, hey, we need some random numbers to be introduced. Okay. What kind of random numbers? Because previously you remember its mean value was 0, and the variance should be equal to delta t. Similarly, there must be some restrictions on this. One restriction is that its time correlation must be some t. I will describe all these things a little later in the next lecture. So it must remember for a while. So in other words, if in DNS you can go and find out. So when you do DNS, you can get this quantity. So when you do DNS and when you track particles, and you can ask how much it remembers the velocity fluctuations. Okay, you can use DNS to calculate this, and usually it happens that for a certain time when it is. So this depends on how long a particle is going to sit inside an eddy. Till it's in an eddy, it will have a certain velocity fluctuation. When it jumps to a different eddy, then it will lose that correlation. So this correlation must be important, because in the Brownian motion, this correlation time was 0. Every time it gets fresh kick. In this case, we need to build in. When you calculate this u double prime, you must remember and calculate it in such a way that whatever you predict in some time step must be correlated to some extent with the previous time step, but it must be uncorrelated with something that was far away, which is longer than, for time period that was longer than this time scale, you shouldn't be correlated. The second thing is that the mean square value, this must be equal to mean square fluid velocity seen by the particle. So in other words, what we are trying to do is that I want to tell you, we are trying to model not the particle velocity. I want to emphasize, we are trying to model the fluid velocity seen by the particle. Okay. There is also another kind of Langevin model. We can straight away say, hey, I want random kicks. In the case of a Brownian motion, particle velocity was random. Here we are saying, well, I'm going to solve the BBO equation. Therefore, what I want is, I want to know how fluid velocity, the effect of the missing turbulence, okay, how does it change over time? So that's the question that we are asking. Okay. Now the model, let me write it for you. The model is very simple. Every time step, this is only change, this what I'm writing here, how much this changes. This is change over one time step. So in other words, this random kick will be added to whatever the random kick that the particle received in the previous time step. Okay, and I don't want to, maybe I will skip that little detail here. dW is the unit random number, in this case unit random number. Okay, it's a vectorial quantity. So in other words, you have to create a random number between -1 to +1 in the x direction, y direction, and the z direction. And for people who are doing Rand's model, you probably are familiar with the closure C0. There is a constant there. There is some value. Okay, and epsilon is nothing but mean dissipation. Okay, so in a Rand's model, you will get this. So this is for Rand's. There is a similar equation for LES, and I'm not going to show that. But you get the point is that this makes sure that you satisfy here this way. Whatever you add, you're kicking the particle with the right amount so that you will get the particle velocity, the fluid velocity fluctuation seen by the particle is the right value. Okay, and it depends on the Rand simulation that you have done. So this is the new kick this is the memory part. Why so? If you only solve this equation, you will find that so in other words, if you don't give any kick, the equation that you solve is that u double prime will decay exponentially with the time scale, this TUC. So in other words, whatever the next time step, the velocity that you're going to have is going to be correlated with what you have plus a little bit of random kick. So this is a very simple, and this is the Langevin model, the simplest Langevin model. So you get input from your RAND simulation, you use the random number, and the two inputs that you need that I talked about are this mean square dissipation value and the time scale of correlation you must know. If you know this, you put them in there and you use this. Every time you will give a little kick to the problem, and in the end, even a RAND simulation, the particle will behave like as if you have done a DNS simulation. Okay, so any questions on that? Yes.
So it's a new kick, why it's not a positive, negative both?
Which one?
The extra part what is coming, that is a random one, right? So it can be positive.
Absolutely. dW is a random number between -1 to +1 or some such. So in other words, it will have both things. It can get a positive kick or a negative kick. In fact, it is a vector quantity, so it will get a positive kick or negative kick in the x direction, y direction, and the z direction. Yeah. Yes.
So this CO epsilon is the what is that exactly?
What it does is, when you go through the calculations, you will find that if you follow this quantity, this u double prime you calculate based on this algorithm, its mean square value will be here. So in an isotropic turbulence, the average dissipation, C0, etc., have been tailored so that you will capture the fluctuating fluid velocity a particle will see when you implement this algorithm, will correctly capture the mean square fluid velocity that it's supposed to capture.
So then this would be a function of the dissipation from the RANs.
Absolutely, yeah. So in other words, if you have a very complex RAND simulation, you look at the point where the particle is sitting. What's my mean dissipation, which is available in a RANS, and RANS model has a C0, a coefficient. If you put those things, then automatically every particle that happens to be there will have a mean square velocity fluctuation given by this. Okay. So in other words, this model has been built to enforce these two restrictions correctly.
So then basically we are adjusting the fluid velocity to match whatever is supposed to be observed.
That's right.
And UC at without the double dashes is the mean velocity we get from our simulation. And this is only the fluctuation. So it's mean square fluctuation rather than mean square fluid velocity.
That's right. So this takes care of whatever turbulence that you did not compute. So in this case, it's all the turbulence because we are talking about RANs. For LES, you have very similar equation, a little bit more complicated. It will try to take care of subgrid turbulence that you neglected.
That will be related to our SGS model, whatever.
Absolutely. Yes. So there you will calculate the SGS, the eddy viscosity will come in, and a similar formula will come. So that when you do a RANS or DNS, everything that you need will come from the RANS, both the mean velocity as well as the information on fluctuation. But one thing that you have to notice, the challenge here is the time scale, correlation time scale. You will not get automatically in a RANS or in a LES. So a lot of what I'm going to talk about is how do we get this time scale, big T. Okay. Any other questions? Again, this is the basic model is from Pope. By the way, I'm not going to say anything. I'm going to leave it empty, but it's in the book. But you can consult Pope, because what I showed there is an isotropic model. The turbulence, that kick in every direction is the same. But in reality, if you are going close to your wall, the kick that you may get in the streamwise direction is different from the wall normal direction than in the And people have worked out all these details, but the basic idea is exactly the same. You will have a time which will keep some memory. The memory could be in the streamwise direction, in the wall normal direction could be different, and a fresh kick of dW, whose amplitude will be based on mean velocity fluctuation in the streamwise transverse, etc. So, anisotropic model is nothing but a more complicated version of what I showed. Okay, so to summarize, part
limitation to it, like where can we use this model and where we cannot use this model?
you can use it everywhere.
Everywhere. Give up any five.
I mean, wherever you did not compute turbulence, and you want to know what that turbulence that you did not compute, what it does to particles, you got to do something. And this is the best approach. You have to give a random kick, but then the random kicks that you're going to give will have the physics in it. The two physics of memory, and the kicks must be of the right kind so that the particle will mimic what it really should be doing. So ultimately the goal is that when you put it in and you move particles in a range, the behavior should be as if we have done a DNS. Yes?
Regarding the computational expensiveness, so DNS is highly computationally expensive compared to other two. So what about the RANs and LES, which will be more computationally expensive?
What is that?
Between RANs and LES, which will be more computationally expensive?
LES will be a lot more expensive, because RANs in a stationary problem, you calculate the steady state. But in LES, since you are computing dynamics of big eddies, you got to do a time dependent simulation. We did very recently this problem. Say for example, we took a room probably bigger than this, 10 meters by 10 meters by 3 meters, and we asked the question, if somebody sneezes or coughs or keeps talking, how the droplets will disperse in this. So we did a LES, and we put because that room was too big for DNS, LES, and we calculated the dynamics of droplets. And we did a RANS where the flow was steady and we put particles, but then we had to put this Langevin model. We put the Langevin model and compared the distribution of droplets that you compute with RANS against LES. The RANS was about 5 to 10 times cheaper, okay, so in that particular problem. So actually it's an excellent question what you're asking. When you do this, even though the RANs may be steady flow, the particles must be dynamically calculated, because this randomness will change from particle to particle. So this RANs with Langevin model will be more expensive, but you get the right behavior. Okay.
So just to conclude, you put the scene in like extra quotes. So what is the significance of fluid velocity seen by the particles?
Fluid velocity seen by the particle is basically telling you what the turbulent eddies are asking the particle to do. So we have an equation, BBO equation tells you that, tell me what the fluid velocity is and I will move the particle. So now we are missing some fluid velocity, that we are not using the correct fluid velocity, so we are sort of faking it.
This is related to the undisturbed flow?
Everything. So you're absolutely, so this is all undisturbed fluid velocity, okay. This is undisturbed fluid velocity. So here what we want is the undisturbed sort of fluid velocity that the particle sees. We are saying that RANS gives me a velocity, it's missing the turbulent information, and I want to stick in the turbulent information, okay. And so we come up with a simple stochastic model for it. Yeah. All right, so I want to go to the next. So one thing before I leave this, I want to emphasize that what we are interested in this one is how the fluid velocity changes, how the fluid velocity at a particle changes as I am tracking the particle. That's what needed here. But another quantity that we earlier talked about, you remember, I don't know, you probably don't remember, yesterday we talked about how the ball is spreading. There what we were talking about is the velocity, 2 times particle velocity, that we are talking about tracking the particle and the particle velocity itself, and that relation is what I want to talk about in the next lecture. First, I want to introduce a bunch of correlations. Okay. Yesterday we talked about, we have a turbulent flow inside a bucket. Let's say we are tracking a particle, and I've drawn it very big, but in reality it's small, and the particle has a velocity v, and the local fluid is moving at some other velocity. This is u of the continuous phase at the particle. So, particle is moving at velocity at that time. This is, let's say, t equal to 0. Now, I want to talk about 2-time correlations. Okay. So, in other words, I am going to talk about how velocity at one time and velocity at another time are correlated. And I am going to talk about 4 of them, not just one, 4 of them, so that you will see how we can, because earlier I said that, you remember, the correlation time is something that we need to know if you want a good model. So, what I am trying to build a case is that, where is that knowledge going to come from? Okay, how do we get it? Okay. So, first thing is that let me introduce, we did this in the last lecture, is Rij. This, I am not going to write it, and I am going to say it in words, is nothing but velocity, particle velocity at some time 0 and particle velocity at a different time okay. So, it is normalized. Okay. So, when z goes to 0, this will be 1. So, if you plot this as a function of z, it will go from 1, it will exponentially die. This is the 2-time correlation, and I have assumed stationarity. That is why I put 0 and z. So, in other words, what I am talking about in this case is, I take particle velocity at time t equal to 0 and particles velocity at some other time z. I have a mixed notation. I should have written I and j here, okay, and in this case it is a amplitude. Okay. So, we correlate the ith velocity of a particle with the jth velocity of a component of a particle's velocity at a different time. Okay. And we yesterday somebody commented that this most likely will be diagonal. In other words, x velocities will correlate, x y velocities may not correlate, y velocities may correlate. Okay. So, in other words, this tensor may be diagonally dominated, and if it is isotropic, the diagonal elements will be exactly the same. Okay. But the important thing is that this is correlation between particle velocity following a particle at 2 different times. Not an easy quantity to compute or experimentally measure, because it requires you to track one particle among million and find its velocity as it moving around. It is a really horrible quantity to deal with, but we want it, because I said that this quantity is the one that will give diffusion coefficient, if you remember last time, and this quantity is a very important quantity, but it is inaccessible. What is really accessible in an experiment is much easier one, is the same 2-time correlation between ith component and the jth component This is something you can calculate. This also will look like this. It will start at 1. It may decay at a different rate. They may not look, they look qualitatively the same, this guy and this guy. So, what is the difference here? This is a second velocity, 2-time velocity correlation I am presenting. Here, we are not moving anywhere. We are staying at the same point. This is called the Eulerian 2-time correlation. And this is the Lagrangian. If you move following a particle, that is called a Lagrangian 2-time velocity correlation. In this case, we are saying put a fixed probe, put there, calculate the ith component of velocity and correlate it with the jth component at a later time. Okay. This is computable. Okay. This is computable and this is hard. So, some of the discussion is, if we know this, can we write this? That is the question. If we know this in a turbulence, okay, the one that you can compute easily, calculate or do experiments, can we use that to tell something about the one that we really want? So, that is the kind of goal that people engage in this business. Okay. And by the way, the time scale, okay, the time scale, well, maybe I will go to the next slide here also. Okay. You can define the time scale. This is the one that we wanted. It's nothing but the area under the curve that I showed in the previous plot. The area under the curve so any time 2-time velocity correlation, you can calculate the area under the curve and that will give you the time scale. So, similarly you can calculate Tij for the Eulerian one. You take that corresponding Rij, which is the 2-time Lagrangian correlation, and you do this integral. Okay. So, really what we want to, I should have said precisely that if this is what you want, you have to connect it to something that you know about. Okay. The Eulerian correlation is what easily people can calculate. Okay. So, the way one goes from here to here in 3 steps. So, we are just 2 minutes. Okay. Just let me finish it. So, the way we connect it is in the following way. Okay. So, here you have a particle and the particle is moving. Okay. This is Eulerian fixed probe, not following anything. So, in other words, you say, well, I start with what experimentally easy to measure, then you say the next thing that you are going to do is you say these notations have some meaning, but I do not want to go through the details. So, what you are saying is that follow the fluid parcel. Okay. This is how people have done. So, I am just telling what others have done. So, you say first I am going to measure at 2 different times ith and the jth component of fluid velocity sitting at the same point. Then you relax and say, okay, well, fine, I will follow the fluid parcel and take the 2 different time velocities. Then you say, I will follow the particle, this is the following the particle, but track fluid velocity. So, in other words, fluid velocity following the particle. And the last thing is that you follow particle and track particle velocity. So you have to go from here to here, here to here, here to here, and when we come back I will say a few more about information about this. So this is how models are being built. Okay. So in other words, if you want to use Langevin model, you will use some model for time scale, some model for fluctuating velocity. There's a lot of details there, but I'm just trying to give you an idea about how people go about developing these models. Okay, and I will tell you the final answer in the next slide, next lecture. Thank you.